I am going to be talking about certain analytical techniques that are used in organic chemistry and biochemistry. So let's start.
We're going to talk about IR spectroscopy. So IR spectroscopy is a chemical analytical method that uses different frequencies of infrared light to detect predictable types of chemical bonds and molecules. It looks for functional groups, so we're dealing with organic compounds. So frequency will cause certain bonds to vibrate, and they can either stretch, twist, wag, or do scissoring motions. And when they do this type of movement, they give off a certain frequency, which feeds back to a computer and processes whatever frequency was given back, and then you understand how the structure is. So if the molecule is symmetrical, like diatomic oxygen, nitrogen, fluorine, you will not be able to see it using IR. So IR depends on asymmetry. So let's break it down. So we have the fingerprint region, and this is where you have a lot of single bonds. You have your carbon-nitrogen, your carbon-carbon, carbon-halogen, carbon-oxygen bond. And that's usually from 0 to like 1500, I would say, yeah. And then the next region, I would consider the double bond region, and this is where you have your carbonyl, your carbon-carbon bond. So when analyzing peaks, right? When analyzing certain parts of IR, I would like to break it down into what wave number is, and the wave number is just some unit of frequency. What is the compound of interest? Is it a carbonyl or is it a double bond carbon? And the peak. So we want to look at the length of the peak and the width of the peak. So for IR, for something in IR spec that's around 1650. It usually for something around 1650, and it's usually medium and sharp. We call that the carbon double bond peak. And for something that's like the carbonyl, it's a wave number around 800. The carbonyl is usually very strong and sharp. That's the carbonyl peak. So if you look at this picture, I would say the sharp peak over here is the carbonyl, and then I would say this peak towards the right of it would be the carbon peak. The fingerprint region, a lot of professors don't really test on it. Usually they care about everything above it. But it really depends on your professor, to be honest. I remember when I took orgo, my professor didn't care about the fingerprint region, so I didn't really learn it that well. But everything past the fingerprint region is usually fair game. So the next important region is the triple bond region, and that's usually from 2200 to about it's usually from 2000 to about 3000. And remember, the double bond region is from 1500 to 2000. So yeah, so the triple bond region is usually 2000, 3000. So the carbon-carbon triple bond and the carbon-nitrogen triple bond are about the same. They're around 2200 to 2300, and they're usually medium and sharp. So remember, medium refers to the length of the peak, and sharp refers to width. So if you see, remember in the cardinal bond that we showed over here, it's medium because it's not as tall as the carbonyl. So, and it is sharp because it's pointy, I guess. And then if you look over here, if you look at the triple bond regions, apparently this graph doesn't show any triple bonds, but it would be similar. It would just basically be like it would be a very small triangle coming out if it was the carbon triple bond or carbon bond. The next important peaks are the single bonds. So we can have a carbon hydrogen bond, and that usually a choppy peak, and depending on what carbon is. So if you have sp3 carbon, it's usually around 2900, 3000. If it's an sp2 carbon, it's usually 3000 to 3150. If it's an sp carbon, it's usually 3150 to 3300. And then the two most important ones are the oxygen. The oxygen is usually weighing around 3200 to 3600, strong and broad. And then the nitrogen is usually 3300, and its peaks correspond to the number of hydrogen it has. The carbon hydrogen bond is usually pretty strong and choppy and sharp. So that is just a quick overview of the IR spec. Things that I think you should memorize definitely would be carbonyls. Remember, carbonyls are 1700 strong and sharp. Oxygens, remember, they're 3200, 3600 broad and strong. Amines, so the NH is usually 3300 medium and sharpish. So the theory behind NMR comes from the spin of a nucleus, and it generates a magnetic field. So without an external applied magnetic field, the nucleus spins at random in directions. But when there is a magnetic field applied, the nuclei align themselves with or against the magnetic field, external magnetic field. So when the external magnetic field is applied, the energy transfer is possible between the ground and excited state of the atom. So when the spin returns to the ground state, the absorbed radio frequency energy is emitted at the same frequency. The emitted radio frequency signal gives the NMR spectrum a visual of how the atom looks. So basically, I'm going to focus on proton NMR. Proton NMR is a powerful instrumental method that identifies protons that are in slightly different electronic environments by inducing magnetic fields and electrons around the nucleus. So if you look at a NMR, the further you are to the left, you are downfield, deshielded. The further you're to the right, you're upfield and shielded. So the more upfield you are and shielded you are, you're at 0, like as the most. And the more downfield you are, the more deshielded you are, you're at 13. So you can use different standards, but the standard that most people use is TMS. And I think TMS is just a silicon with multiple carbons. So electrons usually shield a proton from the effects of NMR, but when you add more electron withdrawing groups like carbonyls, they tend to take away the electron density, so there's less shielding for the protons, and thus there's more effect of the magnetic field by the protons. So the further downfield you go, the more deshielded the proton gets because you're getting more electron withdrawing groups. So there's 4 type information that you get from NMR spectra. One you get is the total number of signals. So the different numbers of signals describe how many different types of hydrogen, whether we have a CH3, a CH2, a CH, or an OH. Second type of information, chemical shift. It's usually the x-axis, and it describes how shielded or deshielded hydrogens are. And this is good because then we understand what neighboring groups are on these hydrogens. Integration. So integration describes the relative ratios of each type of hydrogen. Do we have more methyls of CH3s than CH2s? Do we have more OH than we have CH3, etc.? And then multiplicity describes how close or far the different hydrogens are to one another. So when we look at the first part information, we're looking at the number of signals. There are many signals on each spectrum that are unique, and we call them non-equivalent protons. So equivalent protons are defined as protons that have the same prospect on the molecule. For now, let's assume that hydrogens are bound to the same atom are considered equivalent. And yeah, let me just pause it over here. Right, so the first step, the first information we get is total number of signals. So as many signals you get on the spectrum, and every signal that's unique, not equivalent, you would appear on it. But equivalent protons are defined as protons that have the same effect on the molecule. So let's just say equivalent protons would be hydrogens that are bound to the same atom and have the same effect. So symmetry will reduce the total number of signals. So here's a quick shortcut. If you look at the picture on the right, you would think that you have two signals, right? But if we draw a line down the middle, these protons are exactly the same. So we don't have two signals, we only have one signal because these protons are equivalent. All right. But if we draw, so on NMR, we would just see, like, with respect to these two, we would just see one hydrogen. And then if we go over here on the page on the right, these are not equivalent. Why? If we draw a line in the middle, we can see that this H is close to this OH. And the other one's not close to OH. So by that logic, they're different. So then we have three hydrogens instead of one. They're not equivalent. So it really depends on the side. So the best way to figure out if we have equivalent protons is draw a line in symmetry, and then you count all the non-equivalent protons to give you information about how many signals you're going to get. So that is how you would obtain the number of signals. Remember, chemical shifts is just seeing which protons had better protection against the magnetic field. So the further downfield you are, the more deshielded you are. That means you have an electron withdrawing group, and your proton's not protective as well from the magnetic field, and it's being affected by the magnetic field more. So you get a higher frequency. But if you go towards the right, your magnetic field near a lower number, that means you're shielded. You're more protected from the proton. So here's some things that you should memorize. Carboxylic acids, protons are usually 10 to 13. They're probably the most deshielded. Then if you look at aldehyde, proton is the second most deshielded. It's about 9 to 10. Benzenes, deshielded around 6 to 8 because they resonate. So because it's so highly stable, it takes electrons away from the proton, which would make it more deshielded. Alkanes, which are the least, which are the most shielded. Which are the most shielded would be around 1 to 2, pretty low. And then if you have a carbon, hydrogen, and a Z bond, so a Z could be a halogen or a benzene, etc. So I would say memorize those types of hydrogens that are bound to it. So the next piece of information you get is like multiplicity or splicity. It depends on the n+1 rule. So the best way for me to explain it is looking at this example. So if you look at this example, you see that there's 3 distinct hydrogens, 1, 2, and 3. And you have to look at the neighboring hydrogens around it. So for HA, you look at the left, you see that n is equal to 0. No, you look at the left, you see 0. You look to the right, you see 0. So you can say n is equal to 0. So according to n+1, the peak we would see for this would be a singlet. And because it's a CH3, it should be, well, it does have a carbonyl, so it could be probably a little deshielded. If you look at HB, it's hydrogen B, you see that there's no hydrogens over here, but there's 3 over here, so that means n is equal to 3, n+1 is equal to 4, so that means we would see a quartet of this hydrogen. Next one we would see would be this one. H3, we have two hydrogens over here, it's over here, so N equals 2, plus 1 is 3, so we would see a triplet. If we look at this molecule, we have a hydrogen over here, 1, 2, 3, 4, they're all different colors. So the first hydrogen, N would equal to 2, because this would be CH2, so this would be a triplet. For this hydrogen, N would be equal to what? 2, then plus 3. No, N would be equal to 2, plus another 2. No, I'm sorry. N would be equal to 3 plus 2, which means N is equal to 5. 5 plus 1 is 6. This would be a sextet. And this hydrogen would be N is equal to 2 over here. And 0 for hetero atoms. Any number that cannot be a carbon hydrogen is given to 1. N is equal to 0. So this would just be 2, so this would be a triplet. And then the oxygen would just be a singlet because it's a hetero atom. And N is equal to 0. I'm going to talk a little about distillation. So basically, distillation is generally a concept that focuses on separating two components of a mixture. This is achieved by separating them by phases. So distillation is used to remove one liquid from another liquid by changing it to a gas phase, then make it into liquid again. So basically, it takes advantage of differences in boiling points. So the more volatile component is converted into a gas. So volatile means the one that evaporates faster from liquid or gas. And for the simple distillation, the gas forms that travels through the apparatus away from the apparatus to another component. So a gas will undergo many evaporations and condensations and reevaporation cycles. Each cycle increases the purity of the volatile compound. So basically, simple distillation is good when there's big differences in boiling point. So if I want to evaporate acetone in water, I would do the simple distillation, and then I would do it again. So basically, if I want to increase the purity of my sample, I have to do simple distillation multiple times. Multiple times is good, but a better way for me to separate compounds would be using fraction distillation. So fraction distillation just has these little beads inside, and basically when you do fraction distillation, the compound's converted into a gas, but it's converted to gas, and then it's recondensed in these beads. And when it's recondensed in these beads, it increases the purity because they're constantly recondensing and condensing back and forth in this bead. So by the time it gets to the other component, it's just mainly pure components. So usually, fractional distillation is extremely good, but it reduces the yield of your mixture of your component of your desired result. But you have a much more pure substances, and it's usually mainly used when you have similar boiling points. And simple distillation is usually used when you have a difference of 30 degrees Celsius in boiling points, and fractional distillation is around less than 10 degrees. So the advantage of simple distillation is that it takes a long time. And you have to do multiple simple distillation to get a pure compound. So if you have a ratio of 27:1, they usually means you did a 96% pure compound. But a fractional distillation is basically doing multiple distillation at one time. It increases purity but reduces the yield. Yeah. The next distillation I'll talk about is vacuum distillation. So vacuum distillation is the perfect solution when you have elements that decompose easily. or heat sensitive at atmospheric pressure, or when you have a high boiling points, and at a high boiling point, they usually decompose better, easily. So vacuum distillation is the process of lowering the pressure in a column above the solvent to less than the vapor pressure of the mixture, creating a vacuum, causing the elements with lower vapor pressures to evaporate off. Lowering the pressure below the atmosphere results in a lower temperature requirements to achieve the evaporation for elements to distillate, so lowering the overall heat requirements of the system. Of course, there's trade-offs. When you reduce the system temperature requirements, you have to add equipment to create a vacuum instead of distillation. So this is great for compounds that are sensitive to heat and air, with temperatures of a very high boiling point, and the application is basically to create a vacuum to reduce the temperature at which the compound boils to protect it from decomposition, etc. So we're going to talk about chromatography. So chromatography is basically separation based on a mobile phase, which is most of the time just liquid, and a stationary phase, which is solid. So mobile phase, I think the only exception to chromatography that I know of in which the mobile phase is not liquid is gas chromatography. And this the only time the exception that I know the stationary phase is not solid is gas also, which is liquid. So let's see. So chromatography is a physical separation based on the migration of the mobile phase, which is a liquid, or across the stationary phase, which is a solid. Rate of migration depends on the solute's affinity for the stationary phase. So in the case of TLC, right? So it's a separation. It separates based on polarity. So usually in TLC, like the stationary phase is called the absorbent, and it's always polar. And for TLC, it's usually a silica polymer. And if we put a mixture of compounds and it's polar, it'll have a high affinity to the absorbent, so it won't migrate as much. So the polar is going to be slower. It's going to stay longer because it's going to touch the stationary phase, the solid TLC plate, and not want to leave. But the non-polar component will have a low affinity for the absorbent because it's not attracted to it, so it'll be repulsed from it. It'll have a high migration phase. So the non-polar will be faster, leave faster. It'll be found higher from the TLC plate. So for example, if you have a TLC plate and we spot the TLC with 3 different compounds, one compound's all the way on top, one compound's in the middle, one compound's all the way in the beginning. The compound on the top will probably be a hexane because it's the least polar. And then the middle would be something polar but not that polar, like butanone, a ketone. And then the most polar would be like a benzoic acid. So the more polar you are, the less you're going to move. And to describe how well compounds move, we use something called an RF value, and it compares the migration of each compound, and it's usually the distance of the solvent divided by the distance of the component. So a high RF value usually means that you leave pretty fast. You're probably nonpolar. And if you have a low RF value, that means the compound's polar and stays longer. So column chromatography is similar. It's similar to TLC, but it works with bulk quantities of solute, so a lot of quantities. And remember, a high RF value means you have a short elution time. So it means you get out extremely fast. There's something called high pressured chromatography also, called high pressured liquid chromatography. I don't know. No, it's called high pressure liquid chromatography. I'm sorry, or HPLC, and they use pressures about 400 atm. And it's basically the same principle as column chromatography. So an example would be we have a chromatography. We have hexane and butanone. They're mixed in together. So if you let some time pass, the first compound to elute would probably be hexane because it's more nonpolar than butanone. So that's how you separate two compounds. So remember, high R value means you're nonpolar and you leave fast, and low R value means you stay longer. Last two chromatography is going to be gas chromatography and chiral column chromatography that we're talking about. So gas liquid chromatography works on highly volatile compounds and separates based on boiling point and polarity. So basically, the more volatile your compound, which means the lower the boiling point, it will elute first. So so the more volatile your compound will fly right through the gas chromatographer and elute first. The higher boiling point compound will get stuck and come later on. So you basically have for gas chromatography, basically it's going to be the stationary phase. It's going to be liquid, so the column is going to be coated with some liquid to carry the gas. You're going to insert your mole phase, your gas molecule, and first you're going to see the y-axis is going to be intensity, and the x-axis is going to be retention time. So the first peak you usually see is the gas solvent or the standard. So then usually the first molecules you'll see would be molecules with lower boiling point, so non-polars. So they were converted to gas first, and then later on, the ones that come, the one with the higher retention time will be your higher boiling points, your polar molecules, and they'll elute slower. Areas under the peaks give us relative abundance of each aliquot. And that's all to it. And then chiral chromatography is really simple. It separates based on it's kind of like affinity chromatography, where you basically separate based on your affinity towards one enantiomer. So basically, I'll have a mixture of R and S enantiomer, and I'll have this bead that will bind to a particular type of enantiomer. So in our case, if I only bind to an S enantiomer, the R enantiomer will be eluted first, and the S will remain the beads. And then I can use another liquid to remove the S phase and separate the R and S. So that's how I would separate them. There are some other type of chromatographies that we should talk about. One being size exchange chromatography. Basically, it's a column. You have these beads with these holes on it, and you'll put a liquid into the column chromatography in the column, and it'll separate based on size. So the big compounds will be able to go past these beads that have little circles on them, and they'll leave fast. But the smaller molecular weight compounds will get stuck because they get stuck in these holes, so it takes a little bit longer for them to get out. And then we have ion exchange chromatography, and they separate based on size. So we have two types of ion exchange. We have anion exchange chromatography, and basically we're trying to get anion. So these beads will be covered in positive charge. So when we put these compounds in, the negative charge molecules will bind to the positive charge beads and get stuck there, and then we'll wash them off the beads, and we would have isolated our compounds that have anions. We usually do this for more basic amino acids, more acidic amino acids. And then the cation exchange chromatography, the beads are negatively charged and they'll get stuck to positively charged species, so like basic amino acids. Then we have affinity exchange chromatography. This is usually done with amino affinity, so we'll have some compounds that have a natural affinity towards a certain compound. They'll get stuck in that bead, and they'll wait for everything else to wash off, and then you can wash off whatever compound you got stuck with. And yeah, that's just a quick overview of certain types of chromatographies. The good separation technique is acid-base extraction. So it basically removes chemicals from a mixture by their miscibility in a new solvent or how well they dissolve in or mix in it. So remember, all non-charged molecules begin in the organic layer. So your carboxylic acid, your ammonium, your ketones, your alcohol, they're always in the organic layer. So the goal of acid-base extraction is to ionize the chemical you're targeting by changing the pH, so it will migrate towards the aqueous layer. So if I want to remove a amine from a organic mixture into the aqueous layer, I'll add acid. Acid is not going to mix in the organic layer, so it's in the aqueous layer. And then what happens with amines is that they're going to get a positive charge from it and travel to the aqueous layer. The positive charge won't affect the carboxylic acid, so it's fine. So that's what we can subtract. We can take out amines from the organic layer. And once we do that, we'll have a new layer just filled with carboxylic acid and some hydrocarbons, and we'll separate the amines. So if I want to separate carboxylic acids, I can use a weak or strong base to remove it from the organic layer to aqueous layer, or I can, if it's phenol alcohol, I need to do a strong base to extract it. And then once I add the base in, the base will separate the carboxylic acid by deprotonating it. It won't affect the amines. It'll deprotonate the carboxylic acid or the alcohols. They'll go into aqueous phase, and you can separate them that way. And that's how you would separate it, by acid-base extraction. And again, you should have 3 flasks, one with mainly organic layer, second your amines, third your carboxylic acid. And once again, we separate amines using acid, and we separate carboxylic acids using weak or strong base, and we separate phenols and alcohols using strong bases. And we do that by miscibilities. We're talking about electrophoresis. So we have 2 types of electrophoresis: native gel electrophoresis and SDS. Page gel electrophoresis. So electrophoresis is a method of separating proteins and nucleotides by their size. So samples are placed in wells, and for agarose native gel electrophoresis, they have they create electric field. They go towards the anode via electric current. So smaller fragments travel farther than the larger fragments due to frictional forces. Buffers used to ensure that the polypeptides and nucleotides maintain their electrical charge throughout the migration. So usually if you look at gel electrophoresis, the bigger things will stay near the top, while the smaller things will stay in the bottom. The anode is positive, so the molecules are going towards a more positive state, and the more negative you are, the more on top you are. It's negative and positive. So DNA is usually negatively charged. So it's usually naturally repelled by the cathode end and goes towards the positive end of the anode. So usually you use native gel electrophoresis for very large molecular weights. For SDS, you usually use it for smaller base pairs. So SDS is usually a detergent that binds proteins, and it gives them a negative charge and denatures them, and it denatures them by disrupting the protein-protein interactions, such as hydrogen ionic bonding, disulfide bridges, which makes into the primary structure. And this gives a much higher resolve power for molecular fragments. So we use 5 to 500 base pairs. So the smaller percent of gel you use, the larger the range. So like if you're using 3% gel, you're going to be using 100 to 1,000 base pairs. But if you're using 20% gel, you're using 5 to 100 base pairs. And so the main difference between native gel electrophoresis and SDS would be that SDS is for smaller things and has way more little small lines in it microscopically, versus native gel, which is usually much bigger lines. So definitely a difference. So it separates based on size. Alright, so I'm going to try to attempt to explain how a mass spec works. So basically, mass spectrometers are devices that are used to define a very precise measurement for the mass of a particle. It does this by using electric and magnetic forces, and does it in 4 parts. The first part is ionization. So they'll either make the particle gain an electron or lose an electron so it can become charged, so it can undergo an electric force. So let's say the charge, they took away an electron, so it became positively charged. If we go to the next step, which is the acceleration step, in which the particle will be accelerated through a voltage difference. It will be repelled by the positive charge and attracted the negative charge, so it'll gain speed. And then it'll go to the next chamber, which is the velocity selection chamber. So particles will be filtered out, so they can only the correct velocity can get through this slit. So the velocity selector will make its selection based on something called this equation V is equal to.
Just before I finish, you see in the velocity selector, you have a red line and it curves and hits the wall. You have a blue line that curves and hits the wall. The velocity selector only allows a certain velocity go to hit these detections. That's why these things are hitting, because they're selected for velocity.
E divided by B. I think it's going to be the ratio between the electric field divided by the magnetic field. Once they have the proper speed velocity that they want, the velocity will be deflected out. The particles will deflect and collide, and the collision distance will be used to define the mass. So once it collides, it turns into some curvature from the distance, and using that we can measure the r, or the computer will give us the r value, and we can use the equation r is equal to mv divided by qb to solve for m, and that's how we would find mass using mass spectrometer.